that. So we're going to solve the two ordinary differential equations below that came from the heat equation, from the partial differential equation that was the heat equation. It gives us a little hint here. We want to assume that lambda is positive, and we're going to try to find solutions that satisfy the boundary conditions u of 0t is equal to u of lt is equal to 0. So we're going to try to find solutions that also satisfy that. So let me go ahead and try to solve this first one. This is in terms of t. This is actually really nice. It's a separable first order differential equation. I'm going to move my alpha squared over to the other side. So I've got t prime of t divided by t of t is equal to negative lambda alpha squared. And now I can integrate both sides. I'm going to integrate both sides here. Now the integral, because I have t prime of t over t of t, the integral of that is exactly natural log of t of capital T of t. And that is supposed to be equal to, well, if we integrate the right-hand side, we're integrating with respect to t, so it's just negative lambda alpha squared t plus a constant. And I want to solve for capital T here, so I'm going to raise e to both sides. So I get capital T is equal to e to the negative lambda alpha squared t plus a constant. But remember, this is the same as e to the negative lambda alpha squared t times e to the c, and that e to the c, we'll just think of that as being a k, being another constant k. And so my function t, actually pretty easy to find here, was a constant times e to the negative lambda alpha squared t. Let's hang on to that. We're going to be using it later. So before I go on to the next slide, let me recap what happened on this slide. I'm going to try to solve each one of these ordinary differential equations that come up in the heat equation. And so far I've just tried to solve the one for t. I'll try to solve the one for x on the next slide. But I'm just trying to solve the one for t. So I moved the alpha squared over to the other side. Key observation here is that the derivative of natural log of t would be 1 over t times its derivative. So the integral of t prime of t over t of t is very easy. It's just natural log of capital T of t. Integrate the right-hand side. Since we're integrating with respect to t, I just get negative lambda alpha squared times t plus a constant. Remember, it's very important to add a constant when you're integrating. By the way, if it's been a while since you watched the initial lectures here on Educator on differential equations, might be good to go back and check those out because I'm using stuff that we learned back in those early lectures on differential equations. So to get rid of the natural log, I raised e to both sides here. And now, by the laws of exponents, remember, e to the x plus y is equal to e to the x times e to the y. So since I've got a plus c here, that's like multiplying by e to the c, which is just another constant, so I called it k. And now if you solve for capital T, we get k times e to the negative lambda alpha squared times t. So we still haven't looked at the equation for x at all yet. So that's what we're going to go ahead and do on the next slide. So we're still working on example 5 here. We've solved the equation for t, so that's looking good. We have to solve the equation for x. And now this is a second order linear ordinary differential equation. We had a whole lecture, actually 3 lectures on how to solve these earlier on in the differential equations lecture series here on Educator.com. So if you don't remember how to solve those, here's a really quick review. You look at the characteristic equation, r squared plus lambda is equal to 0. And you think of this x of x, you think of that as being x to the 0th derivative, so I'm going to put r to the 0. So that's why there's no r right here. And so we're trying to solve for lambda. So r squared is equal to negative lambda, and r is equal to the square root of negative lambda, with a plus or minus there. Let me remind you that we were given an assumption here, which was that lambda was bigger than 0. And so that means that negative lambda is less than 0. And so that means the square root of negative lambda is complex. So we're dealing with complex numbers here. It's I times the square root of positive lambda. So we're going to have to deal with complex solutions here. Now, we did talk about what happens when you get complex solutions to the characteristic equation. That was back in one of our earlier lectures here on Educator.com, so go back and check it out if you don't remember. But the short version is that your answers look like sines and cosines. So our R here is plus or minus I times root lambda. And so my solution, x of x, is, I think in our earlier lectures we called it C1 and C2. C1 times the cosine plus C2 times the sine. I'm going to call it A and B for my constants this time. So it's A times, well, remember if you have A plus BI, then you go e to the AT times cosine of BT plus C2 e to the AT times sine of BT. So I'm going to follow that format, except I'm going to change around what I'm calling my constants a little bit. Instead of C1, I'm going to use A and B for C1 and C2. This A is just 0, so you get e to the 0t, which is just 1. So those terms are both 1, and I get cosine of, well, my B is the square root of lambda. So I'm going to go constant times, let me go ahead and call that C1 and C2 so it won't be too confusing. C1 times cosine of the square root of lambda. And my variable here is x, not t, so I'm going to put a x in there, plus C2 times sine of the square root of lambda x. And let me go ahead and change those C1s and C2s and call them A and B. So A cosine the square root of lambda x plus B sine the square root of lambda x. So that's my x of x. And my u, my original function that I was looking for, u of xt, let me remind you what format that had. U of xt was equal to x of x. This was our assumption when we tried to separate the variables, times t of t. And I've already figured out my t of t. There it is right there. And I figured out my x of x. So let me combine those. So that's equal to a cosine the square root of lambda x plus b times the sine of the square root of lambda x, all times k times e to the negative lambda alpha squared t. By the way, that k, I'm going to drop it. And the reason I'm going to drop it is because if I put a k right here, it could be absorbed right into the a and b. So I'm just going to cancel that k out, and I'm going to put e to the negative lambda alpha squared times t. That's my u of xt. But I'm trying to satisfy my two boundary conditions. So let me remind you what those were. My first boundary condition was u of xt, or sorry, u of 0t. Let me label this as a boundary condition because it's probably been a while since you've seen it. This is a boundary condition. This is given to us as part of the differential equation, well, as part of the package along with the differential equation, was that u of 0t had to be equal to 0. So let's see what we get. Remember, that means you're plugging in x is equal to 0. Let's see what we get if we plug in x equals 0 into our u of xt here. So u of 0t is equal to a times cosine of 0 plus b times sine of 0. And all of that gets multiplied by e to the negative lambda alpha squared t, and that's supposed to come out to be 0. So cosine of 0 is just 1. Sine of 0 is even better, it's 0. And so what we get is a times e to the negative lambda alpha squared t is equal to 0. On the strength of that, we can say that a must be equal to 0. And so we won't be needing to use that a term. Now let's look at how we're going to incorporate the other boundary condition, and let me remind you what that was. So my u of xt simplifies down a bit. My u of xt, since our a term has gone away, it's just b times the sine of root lambda x, all of that multiplied by e to the negative lambda alpha squared t. And we're told by our other boundary condition, let me remind you, this came as part of the package when we originally got the differential equation. So our other boundary condition was that u of lt had to be 0. Remember, that represented plugging in x equals L, which was the right-hand end of the rod in the heat equation. So let's plug in x equals L. We get b times sine of root lambda L times e to the negative lambda alpha squared t is equal to 0. Now, we don't want to set b as equal to 0 because otherwise our entire solution disappears. And also, our e to the negative lambda alpha squared t, we don't want that to be 0 because an e function can never be 0, so that's never 0. I don't want to set b to be equal to 0 because otherwise my whole solution disappears. And so what I'm forced to look at is the idea that sine of root lambda L is equal to 0. And so I have to figure out what my possibilities there are to make sine of root lambda L is equal to 0. So sine of what is equal to 0? Well, I know that sine of any multiple of pi, any integer multiple of pi is equal to 0. So this will work if I take root lambda L is equal to an integer multiple of pi, where n is any integer. N is any integer. And so the only thing, remember, L was the length of the rod in the heat equation, so that's a constant. It's established all the way through. We can't change that. So the only thing I can solve for is lambda. And so if I move the L to the other side and square both sides, I get lambda is equal to n squared pi squared over L squared. And this will work for any value of n we choose. So we get one solution for each n. So I'm going to write my x sub n of x. Remember, I had an x of x, but what I'm discovering is that for each value of n, I get a different solution. So, and there's a b there. The b could be anything. So, don't know yet what I want b to be, but bn sine, I have a root lambda L there. So remember, root lambda is n pi over L. Sine of root lambda x, so n pi x over L. And my t is equal to e to the negative, now lambda is rather messy, n squared pi squared over L squared. And I still have an alpha squared t in my exponent for e. So let me extend that. Alpha squared t. So that's my Tn of t. And so ultimately I'm going to get one solution for each n. My u sub n of xt is, remember, you multiply the x of x and the t of t. So I'm going to multiply these two things together. It's b sub n sine of n pi x over L e to the negative n squared pi squared alpha squared t all divided by L squared. Pretty messy, but that's my solution to the heat equation that is still compatible with both of the boundary conditions that you tend to get packaged along with the heat equation. So that was quite a mouthful. Let me go back and recap where everything came from. We started out with, well, we had to solve these two ordinary differential equations for t of t and x of x. So we solved t of t on the previous slide. So on the previous slide, we figured out a form for t of t, and we figured out that it was a constant times e to the negative lambda alpha squared t. That constant, I'm actually going to omit that constant, and the reason is because down at this step, it gets multiplied by x, which has constants attached to it anyway, so I'm going to let that k be absorbed into the constants for the x functions here. So I'm not going to worry about that constant. What I do have to focus on next is solving this ordinary differential equation for x. And I learned how to do that back in our lessons on second order differential equations. We have an earlier lecture on that right here in the Differential Equations lecture series on Educator.com. So if you don't remember how to solve those, just check back the earlier lecture and you'll see that we did a bunch of second order differential equations, and we had a characteristic equation, we had cases where there were real roots, where there were complex roots, where there were repeated roots. So we worked through all those different cases and different lectures. What happens with this one is we get r squared plus lambda is equal to 0. So r squared is negative lambda, and so r turns into the square root of negative lambda. And we were given that lambda was greater than 0. So negative lambda is less than 0. So what we're really trying to do here is take the square root of a negative number, which means we have complex solutions. And we learned before that when we have complex solutions, a plus bi, this is the format of our solution, except we're using slightly different variables here, so you got to translate a little bit. The C1 and C2, I relabeled A and B, and that's a little confusing because it's not the same as this A and B. This A and B, well, the A was just 0 because it's 0 plus or minus I, root lambda. And the B, this B was root lambda. So that's where I got cosine of, that's the B there, and that's the B there. Also, our variable now is x instead of t. We used t before, but now we're using x's. And so, and I also wanted to change the constants C1 and C2. I wanted to call them A and B, a new A and B. So it's a little confusing with the different variables. I apologize for that. There's nothing very deeply mathematical going on. I'm just kind of quoting the solution from the earlier lecture on complex roots. So, we've now found our solution for x of x, but we want to match the boundary conditions. So we want to compile our solution together with our solution from t of t. So remember, this was our guess with separation of variables. U is the product of x and t of t. So here I'm multiplying them together. And now our boundary condition was that u of 0t is equal to 0, which means you're plugging in x equals 0. So I plugged in x equals 0 here. And that, when you plug in x equals 0, you get the cosine of 0 is just 1. The sine of 0 is just 0. And so you get a times e to the something is equal to 0. Well, e to the something, this term, is never equal to 0. So we must have a is equal to 0, which means our whole term here drops out of our solution. So we're just down to the simpler solution, b times the sine term times that exponential term. And now we bring in our second boundary condition, which says that when you plug in x equals L, then you must be getting 0. So if we plug in x equals L here, then we get complicated expression is equal to 0. Now, the e term, again, can't be 0. That can't be 0. I don't want the b term to be 0, because if b is equal to 0, then my entire solution disappears and I just get 0. So I don't want the b to be 0, which means I must have sine equal to 0. And so if sine is equal to 0, then I have to think about what angles have sine 0. And I remember that sine of any multiple or any integer multiple of pi is equal to 0. So that means root lambda L must be n pi for some integer n. And actually this works no matter what n is, as long as it's an integer. So we're going to get a whole family of solutions with different integers. If I solve for lambda, I get lambda is n squared pi squared over L squared. And now I'm just going to plug those back into my solution here. Back in for root lambda here, and back in for lambda here. So the x part gives us root lambda is n pi x over L. The e part, the t part, gives us e to the negative lambda, which is negative n squared pi squared over L squared. And when we multiply those together, I'm putting subscript n's here because remember we're getting different solutions for each value of n. So we're going to have a whole bunch of solutions here. And so we have b sub n times the x part times the t part. So that's our solution to the partial differential equation that also satisfies both boundary conditions. That's actually officially the end of this lecture here, but let me go ahead and give you a little teaser for the next lecture. Let me write down what we just figured out. U sub n of xt is equal to b sub n times sine of n pi x over L. We just figured this out. E to the negative n squared pi squared alpha squared t over L squared. Now, let me remind you what we did there. We're trying to solve the heat equation, and the original heat equation, let me make sure I write it down correctly, was U sub t is equal to alpha squared U sub xx. What we've done now is we've solved that using separation of variables. We also had two boundary conditions, U of 0t is equal to 0, and u of lt is equal to 0. And what we were doing in this example was confirming a solution that satisfied both of those boundary conditions. Now there was one more condition, which was the initial condition, u of x0 is equal to f of x. And what we haven't done yet is satisfied that initial condition. So that's actually going to take quite a bit of work. That's going to be the content of the next couple of lectures here on Educator.com, where we're going to finish off the solution of the heat equation, and we're going to try to make it match that initial condition. So I hope you'll stick around and watch those lectures so we can finish solving the heat equation together. In the meantime, this is the end of our lecture on separation of variables, and I'll just remind you that this is part of the Differential Equations lecture series here on Educator.com. My name is Will Murray. Thanks very much for joining us. Bye-bye.